Thank you. Andrea said, I'm Rob Emanuel. I'm the lead of a project called GeoTrellis that I'll talk a little bit about today. Just to give you an outline of what we'll be covering, I'm going to give a background on some geospatial concepts and then describe a little bit about what LocationTech is, a background on big data frameworks, and then finally get to talking about an overview of LocationTech projects that deal with processing big geodata. So the title of the talk, Processing Geospatial Data at Scale. And I'm going to kind of go through this slowly and parse out those phrases, right? And we're going to start with geospatial data. So what is geospatial data? Geospatial data is at the core of GIS, and GIS is a term that's been thrown around a bit. If you don't know, it's a geographic information system. Geospatial systems is sort of all the same domain, just general label. And for GIS 101, there's two types of data. There's that which is raster data and that which is vector data. So that's a good thing to note. So let's start with raster data. What is raster data? Raster data is basically an arrangement of cells into a grid. And right here we have a raster. It's not very interesting. I mean, it says, okay, column 0, row 0 is yellow, whereas some others are blue. Not very interesting. But what happens when we put it on a map, when we use it to describe a stretch of land on the surface of the Earth, those cells start to take on meaning, right? So now I can make some statements saying like, oh, Philadelphia is mostly yellow, except for this eastern part, which is blue, and it's a little bit in the west, right? So another example of raster data is satellite imagery, right? Because if we have those cells, you can think of those as pixels. And if we start to assign RGB values to them, you start to get an image. So this is a Landsat 8 image that was taken of the area that includes us right now, but it was in like August 17th. Another example of raster data is, so if we want to measure temperature data, it's useful to sort of do that at a lower resolution worldwide. So we can kind of say, okay, if this area is of this certain temperature quality, so we can say that there's been record warmest temperatures in Mexico in October 2012, right? So we're describing the geographic area with this data. The other side is vector data, right? So points, lines, polygons, geometries. So we'll go through some examples. This is a Google search for bars around here, and you see the points where all the bars are. There's one called Scala Backstage, which I think is really interesting because I am a Scala developer, so I'll have to check that out at some point. Vector data also consists of lines, so a road network. This is a road network, a depiction of some road networks in the United States. And you can see that the geometries don't just describe the area, but also can have qualities. Like there's some roads that are red and some roads that are blue. I don't know what that means, but it differentiates them. Here's some German regions, right? And these are polygons. These are outlines that describe an area of land. So another type of vector data. And then if you kind of throw these all together, you can get some pretty complex data. This is a picture of Openstreetmap of this area. And Openstreetmap, for those of you who don't know, I like to just kind of quickly describe it as the Wikipedia of maps, right? It's a collaboratively built up map of the world. And so people who are just logged into the system have built up this map where you see road networks, you see building footprints. You can see that there's no building footprint for the conference center that we're at. So if you wanted to, and you should, you could go online and log into OpenStreetMap and actually edit the building footprint and contribute that to the entire map. All right, so let's look at processing geospatial data. What does that mean? What makes processing geospatial data special? So I like to look at the contains method, which is really simple, right? We have a point and we have a polygon. And we say, is this point in this polygon? And you say, for the triangle case, yes, that's true. For the hexagon case, that's false. And if you just take a minute and try to just think about what an algorithm would be to try to solve this generally, it's actually a pretty hard problem. And for this is a really simple case. You might have 3 points. Like, how do you determine it's in a triangle? But then if I say, OK, here's a multi-polygon that represents India, and here's a set of points retrieve me all of the points that are within that polygon. That's a pretty difficult problem, and it's very specific to a two-dimensional realm, right? So there's specific algorithms that are needed to solve this in a fast manner. There's other operations like a heat map, right? And that's a point to raster, or a vector to raster operation. We have a point data set, and we want to get a map, a raster, of that represents the different intensities of that point data on a map. So this is a map of crime data, which are the points, and then a heat map is created so that we can sort of see the hotspots of where crime is happening. This one, zonal statistics, is actually combining a set of rasters and a polygon to get a number, right? So we have this operation called a weighted overlay or a suitability map, which takes a number of layers over an area and then weights those according to some model preference, combines the layers, and it creates a suitability map, which means that if I were to try to place a building, know where I wanted to build a new building in a city, I might use a suitability map to tell me where I should build that. Now, if I take a polygon and I draw it over a specific area, I can do a zonal statistics calculation to try to figure out some mean weight or some overall score of that area, and that's what you see at the bottom here. So pretty complex calculations made out of sort of simpler calculations. Another geospatial operation is feature extraction, or in the computer vision world, it's known as image segmentation, where we take a raster and we move to a vector, where if you have a satellite image, you might want to extract the road network out and actually get the lines of the road network. So that's a pretty interesting one. All right, processing geospatial data at scale. So what is the scale of this geospatial data that we're talking about when I say like at scale? Just to give you an idea, so Landsat 8, the Landsat program is a satellite program that's a collaboration between the United States Geological Service and NASA, and it's been running since the 70s, but the Landsat 8 satellite has been up since I think 2013. And they've actually put that publicly up on S3. And right now it has over 300,000 scenes at about 800 megabytes per scene. So that's 250 terabytes and counting. Those of you who caught Chris Holmes' talk this morning, they just acquired, I forget what the name, Rapid Eye, I think is his name, and they got petabytes of imagery from them. So satellite imagery is a domain where there's just tons and tons of imagery. OpenStreetMap, the Wikipedia of maps I was talking about, if you download the whole entire world, it's about 617 gigs. Right now, that's uncompressed. And then so Mapbox recently, or maybe actually not so recently, did a blog article about mapping out geotagged tweets. So if you tweet something and you have geolocation enabled, it'll give you a lat long attached to that. So just the tweets that are geotagged over 3 years, it was 3 terabytes of information. So this is the sort of scale that we're talking about. All right, so processing geospatial data at scale. That phrase should sort of make more sense now. All right, I want to talk a little bit about what LocationTech is. LocationTech is a working group inside of the Eclipse Foundation. So Eclipse Foundation is a software foundation that's supporting a lot of open source projects. And there's working groups such as the Scientific Research Working Group, Internet of Things Working Group, and LocationTech, which focus on specific domains. And so this GIS, geospatial domain, is what LocationTech focuses on. And to me, as the lead of a project who joined LocationTech, LocationTech is a place for the project to have a home. It provides support such as like legal support, legal review, some infrastructure support, but it also provides a community for my project to be a part of and a venue to communicate with other developers doing the same sort of thing. So there's a number of LocationTech projects that deal with this idea of processing geospatial data at scale. And here's the 4 logos of those projects. I lie because the Geo Wave logo is, I couldn't find one, so I just made one in GIMP in 2 minutes, and it's horrible, and that's what you get for not having a logo. So hopefully that kickstarts their logo process. But before I get to these projects, I want to talk about processing data at scale, because processing geospatial data at scale is sort of specialized version of just a general problem. And there's frameworks out there that solve the general problem or try to solve the general problem. And I want to talk about 3 of them today: Hadoop, Accumulo, and Spark. So in order to talk about them, I'm going to go back to the early 2000s to the Apache Nutch project. And the Apache Nutch project was an attempt at some developers to create a search engine, like a better search engine than what was going on at the time. It's before Google started really killing it. And they got it working for small data sets. They got it on 1 machine, maybe 2 machines, and it was actually doing pretty well, but it wasn't scalable. They just, they were having a lot of time dealing with a lot of data, a hard time dealing with a lot of data. And then around 2003, Google published some papers that sort of, smashed up the area. A MapReduce paper on a MapReduce programming model for dealing with processing distributed data in a distributed way, and also the Google File System paper, which described a distributed file system. So that if you have a distributed file system, you have a bunch of nodes of a cluster that have different shards of a data set, and then the MapReduce framework or programming model could work on that data in a distributed way. It's really, really great, kind of what the industry needed at the time, so thanks Google. And the developers of Apache Nutch were just like, this is what we needed, let's implement this. And they did so, and in 2006, those general file system and MapReduce programming model pieces were spun out to form Hadoop, the yellow elephant that if you work in big data at all, I'm sure you've seen. So Hadoop allows us to perform this MapReduce programming model on data. So to kind of parse out this diagram, you can think of this as 3 different nodes. And so Hadoop has what's called HDFS, which is a distributed file system. So there might be shards of data on those 3 different nodes. And then you create a map step that maps over the data on each of the nodes into another type of data. And then there's a shuffle step that's shuffles data around the cluster so that everything's kind of on the grouped together how it needs to be processed for the next step. And then there's a reduce step that sort of crunches down that data and gives you your final result. So this was a wild success. Yahoo put a lot of money and development effort behind it, so did a lot of companies. And everybody who started using it was great, including Matej Zaharia, who was working with Hadoop. He contributed some Hadoop code. He was sort of a consultant, and he was a research student at UC Berkeley for his graduate. And he was working with people who were doing machine learning algorithms on MapReduce, on Hadoop. And he was noticing that these algorithms, which are iterative, were just not a good fit for the MapReduce programming model. Because if you're using MapReduce, you have to fit to this specific map and then reduce and then write out your results framework. So he saw that wasn't quite working, and in 2009, he created Spark. So Spark is a Scala project that is his answer to doing some more advanced distributed programming that kind of breaks out of the MapReduce model. And just to see, one of the things that Spark does that's in opposition to Hadoop is this idea of caching data in a memory of a cluster, right? So Hadoop, if we have an iterative algorithm, we have this load step, and then we do the MapReduce, and then we have to write the data back to HDFS, and then for the next iteration, load it up, do the processing, save it, load, save, which is really time consuming, as you can imagine, if you have sort of a tight loop in this iteration. With Spark, you can actually load it out of HDFS or a variety of different backends like Cassandra, S3, Accumulo, and actually cache the RDD, it's the distributed data set, in memory as you perform operations on it. So this provides a huge speed up for a wide variety of algorithms that sort of need this capability. And so that was sort of the original reasoning behind creating Spark, and it's kind of took off into a more general use distributed processing framework that he open sourced, and a lot of people were attracted to it and started working on it. So it's gained a lot in popularity. Commits in the past year have been much more than other big data frameworks. And if you look at the contributors per month in 2015, it just is spiking. So there's a lot of companies that are throwing their support behind this framework. Yeah, and it's an active community. And so Apache Spark is the core framework for the distributed computation engine, but there's an ecosystem on top of it, including a toolkit for executing SQL against Spark backends, a toolkit for doing streaming processing. So if you have streaming data coming in that's in large volumes, Spark can chunk through that. That has a machine learning library and a graph library, and there's actually more that I haven't put up. And then the last general big data framework I want to talk about is Accumulo. And Accumulo's story is that Google again published a paper in 2006, and this is the pattern. Like Google is just like, we did this awesome thing, and then the open source world kind of adjusts. So Bigtable is a NoSQL distributed database that once that paper was published, there were a number of clones, open source clones that were created. Apache HBase, Cassandra, and Accumulo. And Accumulo was created by the NSA in 2008. That's, thanks for open sourcing it, spies. It was donated to the Apache Foundation in 2011, and it graduated to a top-level project in 2012, and then the US government almost shut it down the same year. I just think this is a really interesting little side note. There was a Senate bill that said, there's some law in the US that the government's not allowed to use software if there's a cheaper alternative in a commercial or open source environment. So there was like language in the bill that was like, you have to prove that there's no other database that does this and that Accumulo is a successful open source project. And it's just graduated as a top level Apache project. It's like, that's pretty successful. It was, I don't know, it kind of shows how out of touch the government is. It was, at least at the time. So Accumulo, is, like I said, is a big table clone. The records are stored on HDFS, but there's a lexicographically sorted table index that indexes into the database and allows you to do quick lookups of where the data is and do query retrievals. And so this is a diagram of how the data is distributed, right? If you think about a SQL database, you have a table. If you partition chunks of that table up, you can spread it across the nodes of the cluster and then work on those chunks of the table in parallel. Great. So now I can get back to the LocationTech projects that are dealing with processing geospatial data. And you can see that these Hadoop, Spark, and Accumulo are sort of behind the scenes on these projects because these projects build on top of those technologies. So the first one I want to talk about is GeoGenie, which is formerly called Spatial Hadoop. Spatial Hadoop is like a really descriptive name of what it does, but for legal reasons, it had to switch. What Spatial Hadoop does, or GeoGenie does, is it gives a spatial language capabilities to Hadoop, gives built-in spatial data types, spatial operations, and spatial indexes to Hadoop. So Hadoop natively can't work with these very specifically geospatial data types. So it needs a library like GeoGenie to add those capabilities. So the spatial partitioning techniques in GeoGenie are such that there's indexing mechanisms in database technologies that work with string data or integer data. But with geospatial data, this two-dimensional data, we need to sort of do some trickery and do some interesting specific indexings. And this is this index capabilities of GeoGenie. And this is what an archery index looks like over a large road network, for example. So in order to find a specific road, instead of having to search over each record, it can use these bounding boxes to kind of search over and pick out a specific one in a much faster method. So here's a heat map that was generated by 1 trillion points, and it was generated in 3 hours over a 10-node cluster. So that's kind of flexing some of its might. And then also it can do visualizations sort of like this, where it takes data, creates the maps, and then creates a video out of the maps so that scientists can sort of see, oh, I can visualize the changes out of these very, very large data sets. And that's what a lot of the processing is like we have these giant data collections in the scientific communities, and then how do we actually learn anything from them? Visualization is one of those techniques, but you need something that can actually chunk through the data and create the visualizations. All right, so next project is GeoMesa. And GeoMesa, I like to think GeoMesa as like geospatial capabilities plus Accumulo accessed through GeoServer. GeoServer is a project in the open source geospatial world that exposes data sources and query mechanisms to geospatial data sources. And this allows Accumulo, that big data framework that I was talking about, to have geospatial data types stored in them and indexed in the proper manner. So here's some demo video of what GeoMesa can do. You can take billions of points and query them with a spatial query. You saw a polygon query, and then also can filter on attributes. But it's not a UI, it's really the services behind it. So you can access it through IPython, do things like kernel density, heat map analysis, and the like. One really cool feature that they just added is the ability to use Spark SQL with GeoMesa. So Spark SQL lets you do regular types of SQL queries on data. So you can like query tweets for containing certain words, but this idea of a where clause with a bounding box is a geospatial concept. So only give me the tweets that are located within this like envelope, this like rectangular polygon. And that doesn't come out of the box with Spark SQL, so GeoMesa had to add that capability. Next project I want to talk about is GeoTrails, the one I'm the lead on. GeoTrails is a Scala library for doing geospatial for working with geospatial data types and doing geospatial operations, and it enables Spark with geospatial capabilities. Right now, and historically, we've been focused on raster data, but very soon we'll be working on enabling Spark with vector data types as well. And we provide storage and query mechanisms for HDFS, Accumulo, and S3. There's a tile. The way that GeoTrails distributes operations over rasters is, if you think of the US as one giant raster, you know, maybe this is like a 500,000 by 500,000 pixel raster, which is pretty big. You can't really fit that into the memory of one machine. But if we chunk it out into tiles, we can then take those operations that we need to perform over the whole raster and then perform them over the single tiles in parallel over a cluster. So that's a basic idea of how we do that. And then so if we have spatiotemporal data, which doesn't just have a spatial element, but also has a temporal element, we end up with these time slice tiles. So you can imagine like a set of maps stacked onto each other and then cut up into tiles. And then you have to store that in a distributed data store like Accumulo. And what this lets us do, if we try to do the zonal summary operation that I was talking about earlier, we can query the tiles so that we can get rid of most of the data that we're not working with, retrieve just the tiles that we want to work with, which might be a very large subset of a much larger data set. But you still want to process that in parallel on a cluster. But that filter step really cuts down on some queries and then processes the tiles in a distributed manner. And just to give you some benchmark results, these are from earlier this year. We were working with climate model output data. And so this is USA temperature yearly average. It's about 430 gigs of data, monthly data, and doing a yearly average of the entire country. We did it over a number of EC2 instances, and we found that M3 extra larges, if anybody's doing any cluster work here on Amazon, M3 extra larges are what I've found to be the most performant for the money. They're pretty cheap on the spot market. So this is 40 nodes, 40 node cluster, which with the spot prices of what I looked up when I did this slide, it was $2 an hour. And we were crunching through that much data in under 100 seconds. So a lot of bang for the buck. All right, I'm going to lose that logo. Last project I want to talk about is Geo Wave. And Geo Wave is another project that works with vector data and can produce heat maps. This is an example of GPS data, which is point data, that's collected over time, and you collect enough point data and do kernel density on it, you can actually create a map of road networks that wasn't drawn at all. It's just the amount of points that people, that of GPS points that have been collected actually end up making out the lines of the road. And the way I like to think about Geo Wave is geospatial capabilities added to Accumulo and accessed through GeoServer. So that sounds like a repeat, and it kind of is. It's a little bit of a case of parallel invention. GeoMesa was around, and then the NGA needed a solution for accessing through OGC standards, the distributed geospatial database. So they kind of solve the same problem, but there are some differences between GeoMesa and Geo Wave. Geo Wave aims to be a generic, or to allow for generic backend support. So there's currently work underway to support not only Accumulo, but Apache HBase, which is another big table clone that I had mentioned. Also, a more technical difference is GeoMesa, Geo Wave, and GeoTrellis all use spatial or space-filling curves to index their geospatial data. And GeoMesa uses the Z-order curve, and Geo Wave uses the Hilbert curve. Great. So Geo Wave data, if they're storing tiles, it kind of looks like this, right? So we have a one-dimensional line that if you spread that out, we can kind of call 0, 1, 2, 3, 4. So we create a one-dimensional index off of two-dimensional data by using this space-filling curve so that each one-dimensional index uniquely identifies one point on that two-dimensional space. And space-filling curves are n-dimensional, so if you go to the 3 dimensions, it gets a little more complicated to visualize, right? But this is still the same idea. We're hitting every point in a spread out, like discrete point space in 3 dimensions with a one-dimensionally indexable curve. And so, like I said, GeoTrellis, Geo Wave, and GeoMesa, we're all kind of doing this work on space-filling curves, trying to figure the math out behind it, trying to figure out the best way to do it. So part of us being together in LocationTech allowed us to get together over some beers and say, hey, we're doing this work, why don't we collaborate and create a project where we try to nail what a space-filling curve is on the JVM. And so we started a project called SF Curve, which is a Scala project that basically tries to do that. So we're all trying to push forward the state of the art of doing space-filling curve indexing on big geospatial data. Great, so that is processing geospatial data at scale at LocationTech, and thanks a lot for your time.